All right, let's jump right in. We're going to be talking about a material that is so new and so powerful, it honestly sounds like something straight out of a movie. But it is very, very real, and it's called MXene. So today we're going to break down the science behind this wonder material and see exactly why it's about to change, well, pretty much everything. So what if I told you there's a material that could lead to a sensor, maybe just a simple patch on your skin, that could detect diseases or even track your stress levels just from your sweat? And no, this isn't some far-off sci-fi dream. This is the very near future that's being built right now with the material we're exploring today. So what in the world are MXenes? First off, you say it MXenes, and you can think of them as kind of like the ultimate 2D material. They're these incredibly thin sheets, literally just a few atoms thick. And the two things that make them absolute superstars are their ginormous surface area, which is key for sensing things, and their amazing ability to conduct electricity. Now, here's where it gets really interesting. The way MXenes are made is kind of backward from how we normally build things. We're not adding stuff together. No, a MXene is created by precisely taking something away. It's all about the art of chemical subtraction. It all starts with a material called a max phase. Think of it like a layered chemical sandwich. You've got a metal layer, an A layer, that's usually aluminum, and a carbon or nitrogen layer. The absolute genius here is using chemistry to perfectly etch away just that middle A layer. The book analogy is perfect. Imagine you have a thick book, and you find a way to magically dissolve every single page 10, leaving all the other pages perfectly untouched, but now with a little space between them. That's what's happening here. And you can really see the results of that process right here. On the left, you have that solid, compact max phase. But after the etching process, boom! Look at the right. The material just puffs up into this incredible accordion-like structure. You've literally turned a solid block into a stack of super useful 2D layers, just waiting to be put to work. But, it turns out there's not just one way to pull off this chemical magic. Scientists have actually come up with a whole cookbook of different recipes to create MXenes, and each recipe gives you a slightly different result. So let's start with recipe number 1. This is the OG method, the one that kicked this whole revolution off back in 2011. It's the most direct approach. You just use a really powerful acid. And this is that classic result. You're looking at what happens when you soak the max phase in hydrofluoric acid. The acid just eats away that aluminum layer, and as gases are created, they literally push the layers apart, creating the signature accordion look. It works great, and it's a big but, hydrofluoric acid is seriously nasty stuff. Not something you want to be messing with if you can help it. So yeah, that led researchers to hunt for safer ways to get the job done, and one of the coolest new methods they came up with involves using molten salts instead. Now have a look at this. The structure is a little different, right? It's more of a neat, orderly stack. By heating salts until they become liquid, scientists can get the same etching effect without all the hazards of that dangerous acid. This was a huge step forward for maybe, actually producing this stuff at a large scale someday. But why stop at just safer? The next step in the quest was to find an even more environmentally friendly method, and that led to alkali etching. And this is where it gets really fascinating. When you use a common alkali, you can get totally different shapes. Instead of that accordion stack, you can create these beautiful, super thin nanoribbons. This just goes to show you that the recipe you pick doesn't just change the process, it can completely change the form of the final material. And that opens up a whole new world of applications. When you look at this timeline, the speed of innovation is just incredible. I mean, we're talking about just over a decade. And scientists have gone from one hazardous method to a whole toolkit of safer, greener, and more precise techniques. This field isn't walking, it's sprinting. Okay, so this is a really crucial point. Creating that puffy accordion-like stack is just the beginning. To really truly unlock the power of MXenes, you gotta go one step further. You have to separate all those individual layers. This quote from the source material really says it all. The real magic, the good stuff, it happens when you get down to these single-layer nanosheets. That's when you get the maximum surface area and all the unique chemical properties that make MXenes so incredibly special. So how do you actually peel them apart? It's a pretty clever two-step process. First, you intercalate. It's a big word, but all it means is you wedge some large molecules in between the layers to pry them open a bit and weaken their grip on each other. Then you sonicate it. You blast the whole mixture with high-frequency sound waves, kind of like a microscopic earthquake that just shakes all the individual sheets free. And this is the gorgeous result. The vial on the left, that's what it looks like when it doesn't quite work. It's cloudy, and the material just settles to the bottom. But the vial on the right? That's the jackpot, a stable, dark solution. What you're looking at is basically MXene ink, a liquid full of single-layer sheets that you can now paint or print with to create next-generation electronics. It's wild. So all of this brings us full circle. We've just gone through all this complex, amazing chemistry. But why? What's the point? Well, let's connect it all back to where we started, building those revolutionary sensors. This diagram lays out the entire roadmap. You start with the recipes we just talked about. You do that delamination thing to create the ink, and then use that ink to build the actual sensing devices. And the end goal is huge, detecting critical biomarkers in our bodies for everything from stress monitoring to early disease diagnosis. So what makes MXenes so perfect for this? It really comes down to this combination of superpowers. That massive surface area gives it tons of room to detect molecules. Its excellent conductivity lets it instantly turn that detection into an electrical signal. On top of that, it's biocompatible, safe for our bodies, and it resists fouling, which means it doesn't get all gunked up by all the other stuff in our blood or sweat. And when I say excellent conductivity, I am not messing around. We're talking about 4,600 Siemens per centimeter. To put that in perspective, for a material that you can process from a simple liquid solution, that number is absolutely staggering. It's what makes it so ideal for high-performance electronics. So we've seen how MXenes are made and why they're poised to completely change medical sensing. But with thousands of possible recipes, different metals, different etching methods, the possibilities are just about endless. And that brings us to the final, really exciting question. From clean energy to faster computers, what massive global challenge will this revolutionary material solve next?